Hi kids. This lecture is a little bit different from the other ones. This is actually a skills lecture on a topic that is thoroughly tested on the AP exam, which has to do with designing experiments and then what's called linearizing graphs. This is something that should have technically been covered in your math classes, but what I found is that your math teachers focus on math applications, and in this class you're going to see how this applies to physics and experiments and science. It actually should make you better at math if you really can understand what's going on. But this is a little bit of a slog because it's kind of a math-heavy lecture, and I'm going to be giving you lots of steps and then trying to model it and show with a couple big, long examples. So expect this to be a pretty long lecture. Probably grab yourself some popcorn and hang out, and hopefully you'll review and remind yourself or maybe learn a few new things. So the essential question is, how do scientists design experiments and find kind of a robust scientific defensible result using graphs? So experimentation questions are really common on AP Physics exams. They want you to pretend you're in a lab designing an experiment to try to discover something about the world. And so there's two kind of parts that I would like you to think about when you are approaching these experimentation questions. The first is the experimental design. So how do you explain your experimental setup or decide what the experiment's going to look like? And the second part is analyzing results that we'll get to in a slide or two. So when I'm thinking about the steps behind experimental design, the first thing that I try to do is to decide what are the relevant variables. What are the things that are most important to figure out? And often I'll do this kind of reverse engineering, where I start with what equation do I know I need to be using to figure out the value I want to figure out, and then I'm going to work my way backwards from there. The second thing is to be really clear, explicit about how all the variables interact with each other in your experiment. So we want to know for sure what variable are we trying to find, what's my wanted variable, and then the experiment usually involves manipulating one variable, changing one thing called the independent variable, and measuring something else to see how the relationship between those two variables might say something about a third variable. If you have more than that, more variables relevant in your equation, you've got to make sure that you call them controls, which means that you hold those variable values constant so you're not changing a bunch of things all at once. So then when you're explaining your experiment to, for example, an AP grader, you would want to state clearly how you're going to keep the controls constant, including what tool you use to verify that you're keeping them constant. You're going to state how you would alter your independent variable. So what are you changing and what tool are you using to change it? And then you want to state how you'll measure your dependent variable, including what tool you're going to use to measure it. And then the last thing that you want to do when you're talking about your experiment is to tell them what steps you're going to use to reduce the amount of error. I think you all should be familiar with the idea of error from your science classes. And at minimum, the easiest thing to do to reduce error is just to say, basically, take multiple data points, but there may be other things you can do also as you think about your experiment to reduce the amount of error. So the second part of experimental design questions is the analyzation part, analyzing your data and the results now that you've taken all this data. And usually they're going to ask you to use what's called a linearized graph to actually find your ultimate conclusion. To make a linearized graph, this is just kind of like the to-do list, and I'll show you guys what this looks like in real life in a little bit. But the first thing you've got to do is start with your equation that you know you're going to be using, and you want to rearrange that equation so that it's in slope-intercept form, which is that y equals mx plus b form. So that's a little bit of a test of your algebra, and it might look pretty ugly when you're done, but you've got to somehow massage, wiggle, push, pull, multiply, divide, add, subtract things until it's roughly in this format. And so what this format means is that y is your independent variable, right? So you need to get your independent variable, whatever you decided it was going to be for your experiment, all alone on one side, or at least the only relevant variable on one side of the equation. There might be other constants or control variables with it. That's okay, although I find it slightly preferable to have the variable just by itself. Then on the other side of the equation, the equals mx plus b side, we've got to have the dependent variable and your wanted variable on the other side. The dependent variable is going to end up being the x in this equation, and the wanted variable, whatever you're trying to solve, will probably either be in a product with that variable, in which case it'll be related to the slope, or it'll be in a sum with that, in which case it'll be the intercept, right? So it's either the wanted variable is either going to fit into the M or it's going to fit into the B, depending on what your equation ends up looking like. So that's kind of an important idea. Once you've got your equation in that format, then you might need to do some additional calculations in order to create some XY pairs for graphing. If your equation doesn't look straightforward, where your variables just fit right into those slots, you might have to do some additional calculations. I'll show you what that looks like on our sample problems here. Then the next step is just to go ahead and graph the data. So you'll now have XY, and you guys should be pretty familiar with how to do graphs. So you're going to put XY data pairs on your graph. And if you've done it correctly, this graph should look linear, which means that all the points should line up in some sort of straight line. And the last step is to draw a straight best fit line on your graph. Once we've done that, we're done with our sort of background stuff. We now have to just figure out, how does this graph actually give me the wanted value? And as we said, it's going to be one of two things once we've got our best fit line. Either your wanted value is somehow incorporated in the slope, so you want to take the slope of the graph, or it's going to be somehow in the B, which is the intercept of the graph. So you can pull those values right off the graph, either just manually, you found slope of graph manually, or you can use some sort of linear regression tool. So your calculator does this automatically for you. Google Sheets does it automatically for you. If you took freshman physics this most recent year, we went through that a lot, where it made the equation. That's called a linear regression, and it's a tool to let you figure out these values really quickly. So once you have created this best fit line, then you're able to use the values from that slope intercept form to actually get your wanted value. I'm going to run you through two sample problems and show you how this protocol that I kind of set up a minute ago would allow me to reach my conclusions and the solutions in a way that AP would be really happy with. So the first one kind of comes from either freshman physics or AP Physics 1, depending on what you took. The question is, you have a force probe, an accelerometer, which is a tool that measures acceleration, and a box of unknown mass on a frictionless surface. You would like to determine the mass of the box as accurately as possible using a linearized graph. So you can probably think of lots of ways to find the mass. You could just weigh it on that force probe. But the question specifically tells you to use a linearized graph, which means you're stuck going through this whole big procedure, creating a graph, even though you might think you have a faster way to do it. And the reason we do it with the graph is because the graph actually gives us a much more accurate, data, error-free, precise solution than just picking a couple data points would. So, experimental design, number one. When I look at the tools I have, they lead me to think of what variables those are able to measure, right? I have a force probe, so I can find F. I have an accelerometer, it's easy to find A. And the M is what I want to know. So pretty quickly, hopefully you're jumping to, this is looking a lot like Newton's second law, that A equals F over M equation that we've done in whatever physics class you had, is probably the one that's going to be relevant to this problem. So then I'm going to kind of decide which variables are going to be my independent, dependent, and wanted. Well, I know I want mass. That's what it asked me to determine. So that's my wanted variable. Independent is the one that it's easiest to kind of tinker with and adjust manually. Accelerometers measure acceleration, but they don't really control acceleration, whereas force probes, you can push them harder or lighter and kind of control the force. So I would make the force my independent variable, and my dependent variable acceleration. Those are the only three variables in that equation, so I don't need to have any control variables in this scenario. Step C is kind of to explain what is the experimental setup. So what does this actually look like? And so I would describe what am I doing in this situation and how am I taking my independent data. So I would say put the box on a surface and attach the accelerometer. In that picture on the right, the accelerometer is actually an app on the cell phone. Then you're going to push the accelerometer with varying amounts of force. So we've got that force probe, and we're going to use it to push that box with the accelerometer on it. And then we're going to be measuring the amount of force with the force probe. So that's my independent variable. I'm changing the amount of force I'm going to be using and using the force probe to measure it. The next thing is to explain your dependent value. So how are you getting data out of this? Well, I'm going to take acceleration data at a wide range of force values using the accelerometer. So I'm changing my force, and I'm going to just record what are the acceleration values. Step E has to do with the error. You want to explain what steps you took to reduce error. So in this case, you would want to make sure you're pushing horizontally. If you push at an angle, that's going to change the amount of force. So that would be one thing. And the second thing, as I said, you always want to just add in there this statement because it'll usually get you a point. Collect multiple trials for each force value. So just making sure you have multiple data trials is going to really help reduce the error. So if I actually did this experiment, this would be like a sample data table that I would create. You'll notice that my independent variable is labeled there, force in newtons. So this is the way I set these things up carefully in Google Sheets. I want to have all my label stuff in the top column. I don't want to have newtons written in any of these values because it makes it nearly impossible to graph. So I just put the label, the units up there in the column header. And I took a wide range. I took 6 different force values so that I could make sure that I had kind of a good representative sample. To reduce the error, I took 3 data points for each force reading. So I did 3 trials of force of 1 Newton, 3 trials of 2, 3, 4, 5, and 6. And then I actually averaged those trials out to come up with average acceleration at a force. So I actually am only going to be graphing these 2 columns in yellow. I don't want to graph individual data points because they're not as accurate as graphing the average. So I actually only have 6 pairs of data here that I'm going to eventually be graphing. But I used all this other data to reduce the error that would be in this experiment. All right, so now I have this nice data table, and I need to figure out how to linearize it, how to put it on a graph. Remember that we had that equation, A equals F over M. But the first step is that I need to get that equation into y equals mx plus b format, right? So my y variable in this case actually was acceleration. That was my independent variable. I decided that was going to be independent from the beginning. So it's already over there. If you see the format that I have, the A is already by itself on one side. So that's actually pretty good. I got my independent variable right there. But the dependent value, which is F, is also on the other side with my wanted value. So that's pretty good. The only thing I would sort of rearrange is to make it look like a product instead of like I'm dividing by M. Because the mx plus b format, we have m times x. And so I would really like that to look like something times F plus something. Instead of F being divided by something. But hopefully you all know from math class that multiplying or dividing by M, this is a little confusing because we have M for mass and M for the slope. Hopefully you guys can tell the difference in those M's there. But in any case, we have F over mass, and dividing by mass is the same as multiplying by the reciprocal of mass, or 1 over mass. So I would rearrange my equation to look like A equals 1 over M times F plus 0. So to me, that really looks like y equals mx plus b format. Same equation, didn't have to do a lot, but now I can really see how it would fit into that other format. And that's going to really help me when I analyze my graph and use it linearization. So reminder, the independent variable is A, it's all by itself. The dependent variable is F. It's going to be on the other side of the equation with the wanted variable. And since my wanted variable is in a product with F, that means that it basically fits into the m chunk of that y equals mx plus b, which is the slope of the graph. So when I make this graph, I'm expecting the slope to be equal to 1 over m, which is the value that I'm trying to get. I also know, incidentally, that the b value in this equation should be 0 based on the equation we're expecting, which would tell me that the y-intercept should be 0 when I make it. So the next step is to go ahead and create your graph, and you can do that by hand or you can do it with Google Sheets. I did this with Google Sheets, and you'll see when I graphed acceleration on the y-axis and force on the x-axis, my data lined up in a nice linear graph. I then used the setup, customize setup tool and got into the series and clicked on trend line. So I'm expecting a linear trend line, and I also had it print the equation out as the label for the trend line, which is super useful in this equation, in this application, because this equation right here is actually going to be the thing that gives me the value of that slope that I'm looking for. So I've got my acceleration on the y-axis, force on the x-axis, all my data points, and as we are predicting, the slope on the graph is actually going to be equal to 1 over m, and that's why this equation is going to be really useful. All right, so we just got from that last slide where we had our best fit line and we made it print an equation for us of 0.5 times x plus negative 0.0333. I'm going to rewrite that little equation. So this equation is actually y equals mx plus b format, but it doesn't write the y in for you. I wish it did. But this is y equals m times x plus b for my linear regression. So now I'm going to rewrite that equation with the independent and dependent variables for my experiment, which looks like this. A equals 0.5 times f minus 0.0333. So I've replaced it with the x and y axis variables that I was graphing. And we remember that the slope of the graph, which is 0.5 according to this equation, should be equal to 1 over m, based on the fact that when I put that format, that equation into that format, that was the m value of the equation. So the last step is just to solve for m itself, because we're asked to find the mass, not the reciprocal of the mass. So I know that 1 over m is equal to 0.5, and that tells me my mass, which is 2 kilograms. So we finally got to the conclusion. I know you feel like you probably could have gotten there a lot faster, but this is much more accurate, and it averages out a lot of errors. Incidentally, the intercept, or the b value of this graph, was negative 0.0333. We were expecting it to be 0. It's not quite, but that's pretty darn close to 0. So what's happening here is our error in our data points just caused my intercept to be off a little bit. So that is due to experimental error, and it's pretty close to 0. Why did we go through all this? Well, without using a graph, you'd probably, like I said, just try to calculate mass using one pair of data points. If you did that with all the data that we had a couple slides ago, your answers are somewhere between 1.6 kilograms and 3.3 kilograms, based on whatever data point you happen to choose and the error with that particular data point. Using a linearized graph, you average out the error for all of your data, and you get a much more accurate result without any outliers. So in any case, this is a really important method for scientists to learn. If you want to be taken seriously in the scientific community, you got to be able to linearize graphs and produce results based on a linearized graph. All right, I want to delve into one more sample problem that's a little bit more complicated. So stand up and stretch, pause the video for a few minutes if you need to, because we're going to get right back into it. And this one's from the current unit in optics. So the question is, you would like to determine the focal length of a converging mirror. Design an experiment and use a linearized graph to find the focus. Okay, so I'm expecting you guys to take some data. What kind of data would we be taking? Produce a graph that somehow is a straight line, and use that straight line graph to figure out the focal length. So if I look at the tools that I have, or that I would, what if I had to think about what this experiment would do, I would probably set up an experiment where I have the converging mirror and I have an object in front of it, and it's pretty straightforward to measure the distance from that object to the mirror. And it's pretty straightforward to locate the image of that object. You can use a screen or you can just eyeball it, but finding the image distance is also pretty clear. The focal length is much trickier to measure manually, so that's obviously what we're going to be, that's our wanted variable. When you think about those variables, the equation that should jump out to you that you're going to be linearizing is that thin mirror and thin lens equation that is one of the only ones that we've gotten so far from this unit, which is 1 over SI plus 1 over SO equals 1 over F. In that equation, the wanted value is the focal length. The independent value, so the one that I can control, is probably the object distance, because I can move that object around or move the lens or the mirror around. And the dependent is going to be the image location. So I will be measuring where that image ends up appearing. Again, I don't have to have any control variables because there's only 3 in that equation. The third step kind of explains how we would change our independent variable. So I would set up the mirror on a stand on the table, place an object in front of it, and use a meter stick to measure the distance from the mirror to the object. So that's what's happening here. We got a meter stick and we're going to measure the object distance. The next thing is use a meter stick again to measure the distance from the mirror to the image of the object. So we have this screen that we're projecting an image onto, and we're going to use the meter stick to measure how far away that image is. And then it says at a wide variety of object locations. So I'm moving relative to the object, so I get a bunch of data points, not just a single data point. Talking about error, I would say make sure the mirror is vertical. If it's not, the reflections aren't going to be vertical and not going to end up on the screen. And then the key thing again, as always, collect multiple trials at each object location to make sure we have averaged out our data. Okay, so let's say we've performed our experiment and we have our data table. This data table I didn't want to show all the data this time, so I just put just the two columns that were interesting, the object location and the average image location. I assume that I actually took that image location several times and then averaged it out. But in any case, here's the data that we got. Last time when we made our linearized graph, we were able to just plot that data right on there and it made a linear graph already, right? The slope was a little funny because it was 1 over m instead of m, but the graph itself was really straightforward. If you attempted to graph this data, this is what your graph looks like. And hopefully really quickly when you look at that graph, you know that there is no way that's going to be linear, right? We have not made a linearized graph. There's no way you can draw a straight line through that data set and learn anything about it from the slope or the intercept. So this is where the kind of algebra manipulation of those equations is going to become important. So we can somehow turn our data from this mishmash crazy graph into something that is linear that we can actually learn a result from. So this is what not to do with this data, and then I'll show you what to do with it in a second. Okay, so the question is, how do we take this big mess of data that creates this big ugly graph and turn it into a linear graph? What do we need to do to our data so that that the graph is actually aligned instead of a big jumble of points like it showed before? Well, the key understanding here is that we know what our dependent independent variables for the experiment are, right? Those are the only things that we can really change or measure, is the object distance and the image location. But those don't have to be the things that we graph. We can manipulate those values or do algebra with those values and graph kind of a new value that might create a linear graph. So to figure out what it is that we actually want to graph to make a straight line, I look at my equation, my original equation, and I want to rearrange it into y equals mx plus b format, because that's the equation for a straight line. So if I can graph things that look like that, it should always create a graph that's a straight line. So in that equation, we've already decided that our x value, our independent value that we're changing, is going to be our object location, and our y value has to somehow be related to the image's location, the thing that we're measuring. So I rearranged that equation just by subtracting 1 over SO. And I did that so that the 1 over SI would be the only information that was remaining on the left side of the equation, just like y is the only information on the left side of the equation. You could actually go and solve for SI and isolate that if you want, although it doesn't really matter if SI is by itself as long as the only other stuff in there are constants or variables that are controlled. So I've got that 1 over SI on the left. This is the simplest way to rearrange this in my opinion. And then I've got two chunks on the right. I've got the negative 1 over SO, which is essentially my m times x piece. The m is going to be the negative 1, and the x is going to be the 1 over SO. And then I have this b piece, which is 1 plus f. So I've rearranged it so that my y independent value is something different than just plain old SI. It's actually going to be 1 over SI. So the independent variable that I'm going to be graphing is not just plain old SO, it's actually 1 over SO. The dependent variable I'm going to be graphing is not plain SI, it's 1 over SI. And when I graph those things together, it should create a graph, according to this equation, that has a slope of negative 1, that's the m value from that equation, and the y-intercept, which is the b value from that equation, should end up being 1 over f, and that's what I'm looking for. So this is sort of how I've manipulated that equation to give me the information that I want, which is the focal length. So the last step is that I need to actually calculate these values, because like I said, we can't graph plain old SI and SO. We need to actually graph 1 over SO and 1 over SI. So I take my data table and I add a couple columns and I relabel those guys, 1 over SO and 1 over SI, because those are the actual things that I need to graph to make a straight line. And then I do the calculations. I would just use Google Sheets to do this calculation really quickly, and I'll show you how to do that next year if you don't know how yet. But of course you can always pull out a calculator too and just calculate each data point. So you need to translate those columns into a new derivative column that has the reciprocal of each value, basically. And then when you use your graphing software, whatever it is, these are the things you actually want to graph, right? So this 1 over SO is going to go on your x-axis, and the 1 over SI is going to go on your y-axis in order to create that graph with that y equals mx plus b linear format. So when you do it, voila, there's the result. It's a straight line. So that data that looked like it was all over the place actually does graph a straight line if instead of graphing the data itself, you graph 1 over SI on the x-axis, or 1 over SO on the x-axis and 1 over SI on the y-axis. Now that we've got this lovely linear graph, we actually want to take the last step, which is figuring out what is the focus. So that was the whole goal of this entire experiment. And to do that, we're going to be using the best fit line. So again, I turned on this linear regression fit on Google Sheets, and I had it print out the equation. That equation should be in y equals mx plus b format. So we add a little y equals, and in the equation, that's your m. That x is going to be whatever value you put on your x-axis, and then, of course, that's your b value right there. So the first thing I would do is I would replace the x and y in that equation that's printed with the independent and dependent variables that I graphed, because that's what's on my axes. And so I graphed 1 over SO on the x-axis and 1 over SI on the y-axis. So I just replace those letters in the equation with my actual physics variables. And now my equation looks like this. 1 over SO equals negative 0.988 times 1 over SI plus 0.138. And if you'll remember, that m value, the slope of this graph, we predicted would be -1 based on the equation on the last slide. And it turns out it is. It's negative 0.988. That's really darn close to -1. Probably just a little bit of experimental error is causing it not to be exactly 1. So that's a good kind of confirmation that we made a nice linear graph according to the equation we were expecting. And that intercept value, that 0.138, that's the thing we've been after this entire time. That's the value that's going to tell us eventually the focal length of our device. Because we remember from the equation that that intercept is equal to 1 over f, according to the linearized equation that we predicted. So we now are going to do one last little math step, which is to set up 1 over f equals that 0.138. Use cross multiplication or isolate the f, and you end up getting f is 7.24 centimeters. It's always good to take a second and make sure that your answer is consistent with what you know about the setup. In this case, we know that the mirror itself was creating both virtual and real images based on the positive and negative sizes of those images, or locations of those images. So that positive sign tells me that we're talking about a converging mirror, or that concave mirror. So we could not only tell, what kind of what the focal length is, but actually what kind of device it is as well. So that's pretty interesting. And we can also take a look at the magnification, how that affects how our results actually match up with our prediction of the focal length of the mirror. So there you go, you did it. Okay, so this is actually my first time ever attempting to teach linearization virtually, so I don't really know how this will sit with you guys, but let me just own first thing that some of you feel very comfortable with this, I'm sure. Some of you, this was like, holy cow, and you may be feeling slightly terrified about the prospects of taking AP Physics now because you've seen this kind of level of work. Trust me, you're going to be fine. You're way ahead of last year. You're way ahead of the kids 2 years from now, or 2 years ago, because I've never done this before. I've sort of expected kids to pick it up on the fly, and they've still done really, really well. So I'm hoping that by teaching this kind of explicitly, at least it gives you a first taste of what this is going to be like. And if you didn't get it from this lecture, that's okay, because I'm going to go through this many more times over the course of the year as we start doing experiments. You'll start seeing it come up in problems and labs and all sorts of other opportunities. So you're going to get better and better at this. So if this felt scary to you, please just like take some breaths, send me an email and say, Ms. Nichols, that was really like more than I was ready for, and I will talk you down from it, because I know you guys can do this, and I think that this class is going to be really a really unique experience for you guys to start seeing how math and science connect with each other. So in any case, thank you guys for watching. Please do revisit your essential question, which is how do scientists design experiments and find results using a graph? I didn't put any specific linearization practice out for you guys now because I don't want to overwhelm you guys with too much math, and we're going to get it as the year goes on. So I just wanted to expose you to this for now. But thank you very much for watching.